Alrighty, so we left off talking about nomenclature of hydrocarbons, how to name organic molecules. And we went through these series of steps, these rules on how to systematically name a compound when you see its structure. And we worked through several examples. Now we're going to do the reverse. We're going to draw some molecules based on their name. And we're going to, just like we sort of wrote it in reverse, we're going to build it in reverse. We're going to build it sort of in the same order that we named it. So the way we started, of course, is with the parent chain. So in this first one, 4,4-diethyl octane, right? Octane, that is the parent chain. So I'm going to start with that. And I'm going to do this in line structure or skeletal structure just because it's the easiest. But if it doesn't specify, you can draw it any way that you feel comfortable. So octane, 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. I always double check after I draw. Cool, got the parent chain down. Now I need to draw the substituents. So I've got diethyl, means that I have 2 ethyl groups, and which are 2 carbon groups, but I don't know where to, I need to know where to put them. I need to have them both sticking off of carbon 4. So my ethyl group, so I'm going to count 1, 2, 3, 4 carbons in. It doesn't matter which side you count from when you are drawing the molecule. And so now I need to draw 2 ethyl groups. So 1 ethyl group that's got 2 carbons coming off of it. And here's another ethyl group that has 2 carbons coming off of it. So I've sort of color-coded this, but generally we won't color-code it. We would just draw it all in black and white. And if I could go grayscale to show you that, I would, but I can't. Maybe I'll do the next one all in one color. So let's do that. All right, so 3 ethyl, 2-methyl pentane. Start with the parent chain, which is 5, a straight chain of 5. 1, 2, 3, 4, 5. Then we have a methyl on carbon 2. So I'll call this carbon 2. There's my methyl group. And we have an ethyl on carbon 3. So down here, I've got a 2-carbon substituent coming off. So this would be 3-ethyl 2-methyl pentane. Next, we've got 1-chloro-3-methyl cyclopentane. So my parent chain here is not just the pentane, but also don't forget that cyclo detail. It's a cyclopentane, which means it is connected. It's a ring shape, and it's got 5 sides, so it's a pentagon. Not the best pentagon, but that's what I was intending to draw there. All right, and then we have a couple of substituents coming off of it. We've got a chlorine coming off of carbon 1 and a methyl coming off of carbon 3. When we're drawing it, so where is carbon 1 and where is carbon 3? We get to determine that. Wherever we put carbon, whatever we decide is carbon 1, so I'm just going to say this one here is carbon 1. So there's going to be my chlorine coming off of that. And then carbon 3 can be in either direction. So we can count, I'll put it over, so this is 1. And let's go 2, 3. How about that? And this is our methyl group. And if I'm just drawing it in line structure, then a line is all I need to represent that methyl. All right, so remember that those numbers are the address. It tells you what carbon it's on. It doesn't mean that there are 3 methyl groups and 1 chlorine, right? It just means that there's 1 methyl on the 3 carbon. And then this last one here, we have 3,3-dimethyl-1-hexyne. Hexyne, that suffix "ine" means that it's an alkyne. Remember, alkynes have a triple bond. Alkanes are a single bond, alkenes a double bond, alkynes a triple bond. So hex is 6. So we've got 1, 2, 3, 4, 5, 6. All right. And that triple bond, it's telling us, is at carbon 1. So we'll make this first one where our triple bond is. We make it 3 lines instead of 1 line. We also know that it has 2 methyl groups, dimethyl, meaning there's 2 methyl groups, and they're both sticking off of carbon 3. So if we said this is carbon 1, 2, then here's carbon 3 with 2 methyl groups sticking off of it. I even draw my little balls to show my carbons. All right. In the textbook, you won't see the balls drawn. That's something that I just like to do as a way to mark my carbons so that I don't lose track of them. And I encourage students to do that. It's not wrong to do that, but just know that in the textbook, they will just be lines. You have to sort of know to imagine those dots being there so you can imagine those carbons at the ends and bends. All right, so it's a good idea to practice some of these. Again, it's the kind of thing where it might make sense when you're watching the video and watching someone else do it, but then when you sit down to do it, you have a brain fart. So make sure you practice some of these, especially ones like odd-numbered ones in the textbook where you can look up the answers. So, okay, we know how we've become pretty well versed in being able to draw organic molecules in different ways and even to name them. But now we're going to look at this funny phenomenon with organic molecules, and that is something called isomers. So isomers, the definition of an isomer is it's 2 or more molecules that have the same molecular formula, the same number of carbons and hydrogens and whatever, but different shapes or different connections, ways of connecting those. So for example, over here on the left side, we have butane, a straight chain alkane that has 4 carbons and 10 hydrogens. And to the right here, we have this branched chain one. It's actually called isobutane, but another way that we could name this is 2-methyl propane, where the parent chain is 3 carbons long, it's a propane, and off the second carbon, there's a methyl group. Okay, so these are 2 different molecules, 2 totally different compounds. They'll have the same molecular weight because they have the same molecular formula, the same number of carbons and hydrogens, but they will have different properties. They'll have different boiling points. They'll have different smells. They'll have lots of different properties. And so they are 2 different molecules, but because they have the same molecular formula, they are related. And so that relationship is what we indicate when we say that they are isomers. Iso, by the way, means same. So these are isomers because they have the same molecular formula, but different structures. So same molecular formula, different structures. So a practice problem here is just simply determining in a pair, if you have a pair of molecules, whether or not they are isomers. Are they isomers or are they unrelated? So what we're looking for is, do they have the same molecular formula and different structures? That's the definition. So the first thing we can do is determine what is the molecular formula. So in A, we've got, I'm just going to count carbons first. 1, 2, 3, 4, 5, 6, 7, 8. So this one is C8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so the same number of carbons. We'll count hydrogens. I'm just going to use little yellow dashes to represent the invisible hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Alrighty. So, they have the same molecular formula. Check. Do they have different structures? Yes, they do. If I erase some of my dash marks and stuff here, all right? The first one is a 6-carbon ring with 2 different methyl groups coming off of it. And the second one is a 6-carbon ring with 1 ethyl group coming off of it. Those are different. They would have different names. They're different molecules. So these are isomers. Check. They're isomers. They have the same molecular formula and they have different structures. All right, let's go with B now. So we'll start by figuring out the molecular formula for each. So this one has 1, 2, 3, 4, 5, 6, 7 carbons. And this one has 1, 2, 3, 4, 5, 6 carbons. I don't even need to count the hydrogens. They're not going to have the same molecular formula. And so I don't really need to continue to figure out anything else. These are not related. They don't have the same molecular formula. They're just 2 different branched alkanes with totally different numbers of carbons and hydrogens and different connectivity structures. All right. So those are what we call sort of simple or structural isomers. Just 2-dimensionally looking at them, we can tell they have a different shape. They're connected in different orders. So another question that you might get is you might be given a molecular formula and asked to draw some different isomers of that, okay? So for C6H14, the simplest isomer would just be the straight chain alkane. And I'm going to do this, let's do condensed structure. So CH3, CH2, 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 CH3. That's 1, 2, 3, 4, 5, 6 carbons and 14 hydrogens. So that would be one isomer. Now we can draw some branched versions. Let's draw one that has a pentane for a parent chain. So CH2, 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 CH3. So that's 5 carbons. And we'll stick a methyl group up here. All right. We could do another one with a pentane. CH3, CH2, 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 CH3. But let's say this time we're going to stick it off this guy here. All right, and I did make one little mistake. If it has a branch group, it's not a CH2, it would be a CH. Because this carbon has got something too. It's right and left, a branch point above it, so that's 3 things. 3 carbons is bonded to, so it only has room for 1 H. So these would all be different isomers. Okay, something we can't do. What if I did it like this? If I made 5 carbons, and then I made the branch point here. All right, that would not work. Because what this is the same thing as this. You can't have a branch sticking off the last carbon. All you did was just fold it up or draw the last carbon sticking up. So that is not kosher. Just wanted to show that real quick. So let's go back to the isomer I had before so these are 2 different isomers that have a pentane parent chain and have a methyl group sticking up. We could also do that. We only need to draw 3 isomers. We've done that, but I'm going to keep going. We could draw some isomers with a butane parent chain, 3, and maybe we have 2 methyl groups sticking off of it. I'll make one up and one sticking down. So that would be an isomer, C6H14. Or maybe we do one that's a butane parent chain. And we have an ethyl group sticking off of it. All right, these will all work. What won't work is this. All right, because this is going to be C6H12 if you count the carbons. And so the sort of formula here for a straight chain alkane, you can tell that it's a straight chain alkane because the formula for a straight chain alkane is CnH2n plus 2. So C6, 6 times 2 is 12 plus 2 is 14. So that tells us this needs to be a straight chain. So straight chain alkanes cannot be isomers with cycloalkanes or with alkenes for that matter. So that's sort of a tip for you. If what you're given is the formula for a straight chain alkane, then all of the alkanes you make will have to be straight or branched chains. You can't make any isomers that are in a cyclic form or that have a double bond. The formula for a cycloalkane, I guess I'll write these again. All right, the formula here for a straight chain or branched chain alkane is CnH2n plus 2. So like C6H14 or C7H16, C8H18, and so on and so forth. For cycloalkanes and for alkenes, the formula is CnH2n. So this would be C6H12. A cyclopentane would be C5H10. Okay? So cyclic alkanes and alkenes, they can be isomers of each other. All right, but they cannot be isomers of straight chain alkanes. Fun fact for you there. So this type of a problem is kind of creative. There's usually more than 3 isomers you could draw. Or, there's more isomers you could draw than the number they ask you to draw, but it's just different creative rearrangements of molecules. There's a lot of different ways you can arrange 6 carbons and 14 hydrogens so that it meets the octet rule and forms different shaped molecules. And in the lab for this week, what you're going to basically be doing is designing some molecules. Some of them are isomers. Alrighty, so another type of isomer that's more 3-dimensional, these are called stereoisomers, and these may look the same when drawn, for example, like in condensed structure. But if we look at it in 3 dimensions, we realize that it has different forms. So stereoisomers are a little bit more subtle. There's 2 types of stereoisomers we're going to talk about. The first type are called cis-trans isomers, or sometimes they're called geometric isomers, but I prefer cis-trans. Cis is Latin or Greek, I can never remember, for same, all right? And trans means opposite. And so what we mean is if we have a molecule that's locked in place. Now remember we said that if you have a single bond, single bonds can rotate. So if you have a molecule that looks like this, all right, an alkane, a simple alkane, you can rotate this carbon and this methyl group here, and it can spin, and those hydrogens can spin around, and same thing with the other one. Because this single bond, you can rotate around it, just like if you had 2 balls connected with a pencil, you could spin them, all right? But if those 2 carbons are connected by a double bond, okay, you can't spin them. Think of 2 balls that are connected with 2 pencils. There's no rotation, all right? There's no rotation around that double bond. It's stuck in place. And so, if we have a scenario where we have 2 carbons that are double bonded together, and in one molecule, they've got methyl groups sticking up. Both of those methyl groups are sticking up. And in another one of the methyl groups is sticking down and the other is sticking up in the other direction. All right, those are actually 2 different molecules. If that was a single bond, then those methyl groups could rotate. And so the same molecule could sometimes have it sticking up and sometimes have it sticking down. But when there's a double bond there, it gets locked in place. And so those are two actually different isomers of the same molecule. So the one where the two groups, the two methyl groups, are on the same side of the double bond. So I drew that sort of dotted red line to indicate, sort of to cut through the double bond. So to sort of extend the double bond, so we could see that in the first one here on the left, those two methyl groups are both above the double bond. They're on the same side of the molecule. So we call this the cis isomer, cis being same. In the one on the right, we have a methyl group on one side of the double bond and the other methyl group on the other side. They're on opposite sides of the double bond, so this is the trans isomer. We see the same thing with ringed or cyclic alkanes. Again, you can't rotate, you can't twist this ring. It's locked in that two-dimensional shape. Okay, so if you have groups sticking off of the ring, all right, and they're sticking in the same direction, remember when we talked about, we did a lab on the computer where we looked at these wedge and dash lines. So remember, a dash line just means that that group is pointing behind that ring or sort of sticking into the paper. And if it's solid, it means it's coming out of the paper or it's in front of the paper. So the important thing to note here is that if one is solid and one is dashed, they're going in opposite directions. But if they're both solid or both dashed, they're in the same direction or on the same side. So in this case, they're both dashed. So these are on the same, going on the same direction or the same side of the ring, so they're cis. And these are going in opposite directions on opposite sides of the ring. So this would be the trans isomer. All right, so cis and trans isomers only exist if there's an alkene, a double bond, or a cycloalkane, a ring, because those things can't rotate, and so they get locked in those shapes permanently. And so that makes those two isomers actually different molecules. So let's just identify each of these. We'll do a practice problem. Identify each of these alkenes or cycloalkanes as either cis, same, or trans, opposite. All right, so in this first molecule, we are ignoring this double bond right here, all right, because it's between a carbon and an oxygen. That's not an alkene. That bond has a different name. The alkene is this double bond right here. Okay, so we're trying to determine, if I just sort of draw a line through this bond, okay, then we look at these sort of groups. There's one group over here on this side and one group over here on this side. These are on opposite sides of that double bond. So this molecule is a trans isomer. All right. In the second one over here, if I just kind of extend a line here through this double bond, I can see that both of these groups are on the same side of the double bond. So this one is the cis isomer. Go down to the bottom left. The double bond is right here. If I just extend it, make a line, I can see that this carbon group is on the top. This carbon group is on the bottom. Hydrogens, remember, hydrogens are invisible in skeletal structure. They're not considered a group by themselves, so we're just going to ignore them. The groups, the substituents, are the ones that contain carbon or something else. So these are on opposite sides. This would be a trans isomer. And in this ring here, they are both wedges, all right? Both of those groups are coming out in the same direction. So they would be cis. It doesn't matter that they're different groups. In all of these, the groups are different things. So it doesn't matter if they're the same or different groups. What matters is the direction. What are they sticking on the same side of the double bond or the same side of the ring? Then they're cis. If they're opposite sides, then they are trans. So there might be some problems in the homework where you just have to identify whether isomers are cis or trans. Another type of three-dimensional isomer or stereoisomer is called an enantiomer. Sometimes we call these optical isomers, and that has to do with the physics of them. That when you shine a light or something through them, they rotate the light in different directions. So that's the optical part. I can't explain it because I'm not great at physics. But what I will tell you, fun fact, is the person who discovered these optical isomers or enantiomers was actually Louis Pasteur, who's more well known as a microbiologist, but he was also a chemist and he did have some important chemistry discoveries, including enantiomers. So, enantiomers, the definition of an enantiomer is it's two compounds that have the same molecular formula. They're isomers. They have the same groups, but they are mirror images of each other that are not superimposable. So a great analogy here is your hands. Your right hand and your left hand, you hold them together like you're clapping, all right? And they are perfect mirror images of each other. Your thumbs line up, your middle fingers line up, your pinkies line up, right? But if you try to put your hands on top of each other, so like palm to back, all right, they don't line up. Your thumbs stick out because your right hand and your left hand have different handedness. If you try to wear a right-handed baseball glove on your left hand, it won't fit, all right? So your hands have this handedness. They are mirror images, but they are not superimposable. They're mirror images of each other. They're opposites of each other. And so there are molecules that have that same handedness. We call these molecules, we say that they are chiral. Chiral is actually Greek, comes from the Greek word for hand. So chiral is just a Greek way of saying handedness. So a molecule is chiral if it has a carbon with 4 different things, 4 different substituents bonded to it. So in this case, we have a carbon in the center, and it has a hydrogen, a hydroxide, OH, or an alcohol group, a methyl group, CH3, and an ethyl group, C2H5. 4 different things. They are mirror images of each other, but they are not superimposable. On this one, these 2 groups are flipped, and that makes them not superimposable. So we have a right-handed version and a left-handed version of the molecule. There's different ways. Again, chemists just sometimes can't decide on naming systems. So there's 3 different naming systems for enantiomers. Sometimes you'll see them labeled L and D, left and right. So that stands for levulo and dextro, which is left and right in Latin. Sometimes you see them as S and R for right and S for left. I don't know what S stands for. And the other one is positive and negative. So positive for the right-handed version, negative for the left-handed version. I won't test you on that, but just know, and you'll see in my examples on the future slides, you'll see a couple of these different naming systems. So the importance of enantiomers is they're really not important in chemistry because enantiomers have the exact same chemical properties, but they have different biological properties. So in chemistry, enantiomers are kind of like they're identical twins for all intents and purposes in chemistry. But you enter a biological system with enzymes, and enzymes are very specific to certain enantiomers. Similarly to how your shoes are specific to which feet they go on, or gloves are specific to which feet they go on. So things that have handedness often fit into something that has handedness. And in biochemistry and biological systems, enzymes are catalysts that will bind to molecules of the substrates, and they have very specific binding sites. So they will be specific for one enantiomer or another. We call this chiral recognition. This is just a little practice problem looking at chiral molecules that I'll come back to in a second in the next video. But I just want to show you that with chiral molecules, it's very important because a lot of drugs that we generate are chiral molecules. They're molecules that have enantiomers. And when we synthesize them in the lab, we end up with a 50-50 mix of the right-handed and left-handed version when you synthesize them. We call that a racemic mixture. And that means that you actually have 2 different drugs in that pill. You have each enantiomer. So there's two consequences of that potentially. Maybe one enantiomer has no activity and the other one is the one that acts as the drug, and that's fine. Propranolol is an example of that. But there can be negative consequences that I'll address in the next video because I've run out of time.